A lot of the math can just be solved by drawing out a network and seeing actually how it would work, right? Just try to architect it in your head. So for a contended network that you're doing collision avoidance, right? It means you have to seize the line. So we have this diagram. So A, B, and C. The network, the maximum network length is your length, which is 100 meters, right? So the furthest computer would be at 0, and this would be at 100, right? So in this network, right, even though there are some computers that are shorter, in order to ensure that this works properly, right, to seize out the line, this guy has to send a signal that travels all the way across the line, right? And then to contend that in case this guy that was farthest away, at the exact same time, sent a signal, right? You also have to, exact same time as this arrived, he sent a signal, right, that came back here. So just before he received it, because in collision avoidance you wouldn't send if you were hearing it, right? Then it sends back, right? So in order for A to know that nobody has the line, you have to wait twice the length, right? So now let's think about how you would figure out a problem like, hey, how long does it take to transmit, right? So to seize the line, right, you have 2 times the length of the network over propagation. So if this was, for instance, this was a wire network that propagated at 2/3 the speed of light, right? Which is, or we did air network, right? So it's an air network that propagates the speed of light at 100 meters. It would be 1 over 3 times 10 to the 6th. Would be the one way, right? And then it would be double that. So that's your seize time. Now, for your original question, you get to send at 10 megabits per second, right? Or you get to send at 1 gigabit per second, you're gonna send at 10 meg 5, right? And then we decided that took 0.08 seconds, right? So 0.8 to put on the line, right? And then of course the last frame arrives the delay again, right? So now we have the length over propagation.
Can you use another marker?
It's a terrible marker. I don't know who I got that from. So,
Jerks.
I don't know. Touche. So now we have the length over propagation again, right? And then to get an acknowledgement, we have to do the same thing again, right? Because an acknowledgement is nothing special, it's still sending a packet. So to get the acknowledgement, this guy would have to seize the line again, right? And then this time your acknowledgement is presumably shorter than what your packet was. So, but it's whatever, it would be your ACK size over bandwidth, right? And then plus 1 over P again, or L over P again, right? And that's just to send it all over and get the acknowledgement. I thought I seriously forgot my book with all this stuff in it. So since we're on that subject and everything's drawn on the board, that was question 15 out of chapter 4. In chapter 4, question 15 says you have a 1 kilometer long, 10 megabit per second CSMA CD LAN. It says it's not 802.3 because 802.3 doesn't seize a line, right? So remember, original 802.3 Ethernet just talks. And then if something happens, it stops talking and there's random back off, right? So, has a propagation speed of 200 meters per microsecond. Repeaters are not allowed in the system, right? That means that your network is simply this long and there's no like any time added on from storing it in a buffer and pushing it back out. Data frames are 256 bits long, including 32 bits of header, checksum, and other overhead. The first bit slot after successful transmission is reserved for the receiver to capture the channel in order to send a 32-bit acknowledgement frame. What's the effective data rate, excluding overhead, assuming there are no collisions? Seems super complicated, but let's think about it. This is back to the same problem. All right, A is going to talk to B. How long is our cable? 1 kilometer, right? So this is 1 kilometer. Our propagation speed is 200 microseconds. Right? 200 meters per microsecond. So it takes, the delay in this case, since it's 200 meters in a microsecond, is to get 200 meters, or to get to a kilometer, that's 5 microseconds, right? All right. And so, of course, it takes, again, seizure takes twice that, right? So let's start, our first seizure is 10 microseconds. And then we also had some other information in there. It was a 256-bit frame over 10 megabits per second, right? 10 megabits per second. So we had a 256-bit frame, right, and 10 megabits per second. So that is 256 bits divided by 10 times 10 to the 6th bits per second. And so we get 25.6 microseconds to send it. That is to put it on the wire. Of course, that's just to get it on the wire. That means that we got to get the last little bit that gets put on the wire. It still has to traverse the entire network, right? So this was 2D, right? And this was, let's see, let's just put frame size or bandwidth. And now it's D, right, for the last bit to get across. So now it's plus 5 microseconds again. And then we have to get the ACK. It has to seize the line again. 10 microseconds. And then 3.2 microseconds to get across because it's 32 bits divided by 10 times 10 to the 6th bits per second. So it's 0.32 microseconds again. And then, of course, it still takes 5 microseconds to get to the end. You add all those up, it is 58.8 microseconds. So now the question is, what's the effective bandwidth of this? So remember, it was a 10 megabit bandwidth, real bandwidth. What's the effective bandwidth? And the effective bandwidth is we can send, remember, it's 224 data bits, right, because of all the stuff that it said was in the header. And we can send that every 58.8 microseconds, which is 224 times 10 to the 6th over 58.8 which is 3.8 times 10 to the 6th, which equals 3.8 megabits per second. So it's less than half for real bandwidth. So any questions on that? So keep in mind, just draw out the network. So imagine, for instance, imagine we had this network A, B, and C, and D. And these aren't hosts anymore, these are routers or switches or however you want to think of it, right? So you have A, B, C, and D, and we are going to send your original, remember we sent all of this at once the last time, so there was no like, continuous acknowledgement, stop and wait problems, nothing. We sent all of this. And because it was a computer-to-computer network, that's fast. What would happen if we were to send all of that with this type of network?
Would it B have to then see the C's line to C, and then C would have to see?
It would be awful, right? Yes. Right. Not only that, it couldn't seize the line to transmit the packet until all 10 megs had arrived. So there is a balance between having large packets, which tends to send lots of information, right, with a router into a networking device that sits in the middle, having to be able to receive all that information before it can send it again. Right? It has to fill the buffer up, construct the packet before it can move it off to the other line. Particularly if like these are different, and that would, so it would theoretically, if these were all the same type of network, right, the moment you receive one bit, you can kind of just start shoving it off to the next network, maybe. You might have some problems in timing if something went wrong, but theoretically you could manage something like that. But if they were different data link and you had to change the headers, right, you gotta have all the information before you can change the headers and send it off again.
So you just manage buffer size then?
Huh?
Is that buffer size on the router that manages that? When you have big packets or?
Sure, well, it's that, but it's the entire design of the network, right? So the question is, like, if you had a computer-to-computer network, would it be more efficient to send a 10 million byte packet? And the answer is probably yes. It would probably be more efficient. You might run into some problems if the network had any kind of errors in it at all, because you wouldn't know the error until the whole thing got across. Right, but like, let's say you're going to send it to like the Mars probe, right? So it's just you and the Mars probe talking. There's nobody else on this network. There's no contention. You don't have to worry about and maybe you hit a satellite in space and then you send it through space, so the noise is really low, right? So it might make sense to send a 10 meg packet so long as there's a crap ton of error correction in it, right? Because you don't really have time to retransmit, because it takes 20, 30, 40 seconds, however long it takes to get there and get back, depending on how far Earth and Mars are apart at the same time, right? So you design your network differently. Versus we are going to have like Ethernet, right? Well, when Ethernet moves across the wire, it goes to the first switch, gets stored because of the buffering process that we talked about, it gets stored entirely in that switch, right, before it gets sent off the next line. It has to, right? So what happens now if you send 10 meg packets? Well, it would take all the time to transmit that 10 meg packet, arrive at the switch, and then all the time to send the 10 meg packet again, arrive at the next switch, and then all the time to send the 10 meg packet again and arrive at the next switch, right? So it's literally, so in this ABCD scenario, it's literally, you gotta cross 3 links, so it's 3 times whatever it takes to send that packet. But if you made the packet small, then it would essentially be 1 time, particularly if you made them really small, and there was no axe or anything that were going there, it would simply be the equivalent of sending kind of like A directly to D if the packets are small. So you gotta think of this, how do the packets arrive? And how do they get sent back off?
Is that the same math like pipelining? Like in the CPU processor?
So in pipelining, for the CPU, what they do is they load what they think is going to be the next instruction. Yeah.
Okay.
But it's somewhat the idea is that what you're trying to achieve is the same thing, right? You're trying to do concurrent execution in the CPU. Here you're trying to do concurrent sending, right? You don't want when you send that first packet, you would like the other links to be used also, right? As things go across, you don't want it to be, we're gonna use this link and finish with that, and then we're gonna use this link and finish with that, and we're gonna use this link and finish with that. It would be nice to use all of them at the same time so that you can get across. So for the homework, question 3 was byte stuffing. In a simple byte stuffing, we didn't have any zoring or anything. You're gonna send A, this one's better, B, escape, C, escape, F, F, D, where F and the F's and E's aren't bytes, they're escape characters. And flags. So E is the escape, F is the flag. So we're gonna send that. Well, the rule is every time you see an escape, you escape it. Every time you see a flag, you escape it. That's it. So you send A, B, escape, escape to account for that escape, C, escape, escape to account for that escape, escape flag to count for that flag, escape flag to count for that flag, and D. It's just as simple as that. So encoding it is really simple. Decoding it is also simple, but you got to kind of have a forward look ahead. So in an algorithm, if you were decoding this, right, you would pull in A, pull in B, because neither one of those specials, then you would pull in E and you would have like a forward look ahead. So like a pointer +1, right, to see if this is E. If it is E, then you just keep this E, right? If not, then it's an escape. So number 9 was sending a Hamming code. The code was, or the data that we were sending was 1101 0011 0011 0101, 16 bytes long, or bits long. So it's 16 bits. That means we're going to need a Is that the code, or is that the answer? That was the answer.
That's the pattern, the message pattern.
Okay, okay.
Yeah, that's right, that's the pattern.
All right, so I ran out of space. So since we're going to have, it's 16 bits, that means that we have to have 1, 2, 3, 4, 5 extra bits to encode it properly, right? Because we are reserving to the 0, to the first, to the second, to the third, and to the fourth. And so we're going to encode that. Well, let's go ahead and put them all in their places. So the first data bit's here. Second data bit is here, 1, 0, 1. That's special. 0, 0, 1, 1. 0, 0, 1, 1, because that one's special. 0, 1, 0, 1. And so the first one is all odd numbers, right? So if we go through and count all the odd numbers of, let's see, yes, so that's 0, 1, 0, 1, 0, 1, 0. So that's 0. And then the next one is what? It's not actually not all evens. It's all the things that contain 2. So, and that would be 2 in binary. So essentially it is 2 to the x to 2 to the x plus 1, where x can be anything but 0. Right? So that would be 2 and 3, 6 and 7, 10, 11, 14, 15, and 18 and 19. So 2 to the x to the 2 to the x, that doesn't make it easier? Okay, sorry. So it would be this. Any number format that is in binary, where this one is 1. Anything else can be anything else. So the 1 bit is set, or the 2 bit is set, right? So so that is 2 and 3, 5 and 6, right? 8 and, or 2 and 3, 6 and 7, 10, 11, 14, 15, 18, 19. 21 for that matter. So if we go through and add all of those together, it is 1. 4 is the same thing. You guys don't like my little cheat. It's to the 2x to the 2x plus 2, or 3. Still not helping, is it? All right. So it's everything with the 4-bit set. 4, 5, 6, 7, 12, 13, 14, 15, 20, 21, 22, 23, even though 22 and 23 are not in our code. Right? So starting with 4, repeating with 4s, and skipping 4s. Is that any better? So the first one was starting with 2, repeating twice, and skipping twice. So this one is starting with 4 times, skip 4, 4 times, skip 4, 4 times, right? And so if you put all those together, that's a 1. And then the next one, 8, is starting with 8 times, skipping 8, so forth. So it's 8, 9, 10, 11, 12, 13, 14, and 15, and then it skips way past 21. 8 is also 1. And 16 is starting with 16, repeating 16 times, skipping 16, that's a 1. And that's your answer. All right, 27. The distance from Earth to a distant planet is approximately 10 times or 9 times 10 to the 10th meters. What is the channel utilization if a stop and wait protocol is used for frame transmission on a 64 megabit point-to-point link? Assume the frame size is 32 kilobytes and the speed of light is 3 times 10 to the 8th meters per second. All right. So, what's the information that we had?
Distance,
Our distance, which is what?
9 times 10 to the 10th meters,
Really far away.
64 megabits, point to point. Data rate,
Is 64 megabits.
64. And then our size is 30 kb or 256 kbits. And then we have the speed of light.
And then C, which is always the same, right? So let's figure this out. How long does it take to get a byte across from one to the other? What is that? Or transmission delay, right? So this is distance. So I normally use D as delay. What's our delay equal?
Frames over the data rate.
4 milliseconds. 256 divided by 64.
Bandwidth over distance.
It's, no, our delay is just distance, right?
256 divided by.
It is
We're talking about the propagation
Distance.
the propagation delay.
Oh, that's-
right?
Oh, you
Speed of
said, you
light.
said transmission delay.
Yeah, I did.
That's what I was.
I threw it out.
Oh,
That was
it's-
transmission.
So it's distance over, or delay is distance over speed, right? So
Yeah, so
9
9 times
times
10 to the 10th.
10 to the 10th over 3 times 10 to the 8th,
So that's
right?
300.
Which is what?
300 seconds.
300 seconds.
That's the propagation of light.
That's our propagation delay. Right? What else can we easily figure out?
Transmission delay.
Our transmission delay.
That's where I was going. 256 divided by 64.
So we have 256 divided by 64.
What's 256?
It's the translation of 32 kb bytes. Like
It's 32 kilobytes, is 256 bits, kilobits.
I don't know if I need to do that, but.
It is kilobits, not kilobytes.
So it was 32 kilobytes, which is also times 8. 32 times 8 is 256 kilobits.
Oh, okay.
And we have a 64 megabit channel. All right? So, we have the time to put in the air, right? Since this is clearly not going over wire, right? So the time to put in the air is what?
Frame size over the bandwidth.
Yes, 256 kilobits over 64 megabits. Which is what? 4 milliseconds?
Or 0.004 seconds.
Yeah, 4 milliseconds, all right? Given the transmission time, I'm pretty sure we're gonna be able to just ignore that value altogether. Right, so, So how long does it take to transmit the frame from one end to the other? It takes our delay, right? So what's our time to get that 256 packet or frame size? What's this frame size to get to the other distant planet? Right, so that is 256 kilobits every 300 seconds, right? Which is 0.8533 bits per second. Of course, we have to get to the other side and back, right? So it's double that, right? So it's double this in seconds, so it would be by 600 seconds. So it's 0.4226 repeating seconds. So that's the hard way to do it. There's an easier formula if you looked around, and that is window size over 1 plus 2 times the bandwidth delay product. And if you do that, you'll get something super close to that. The reason the 1 is stuck in there is because technically when you first start transmitting the first bit, that doesn't count for the first window. So the question was,
Channel utilization.
was the channel utilization, right? Channel utilization, it takes 0.4, we send 0.42266 bits per second on our 64 megabit per second channel. Utilization is pretty small.
So how did you get bandwidth delay again?
So bandwidth delay product is used to is usually used to determine frame size, which are optimal frame size, right? Because usually you want to fill the network to get that. I don't know if bandwidth delay product is applicable here because that number would be really, really, really large, right? Because you have a 300-second transmission time.
That's how I use the cell from, is 150,000.
Huh?
It was 150,000, the bandwidth, the bandwidth delay product, or how many frames you need to fill up the line?
Yeah, you would need 150,000 frames to fill up the line at that frame size. Not that it's in any way realistic whatsoever, because you would also be getting responses that far away also. But anyway, 15 we did, and 24. 24 was a little not intuitive. How many people went and looked at the book for 24? I gave everybody permission to look at the book. All right, so it's not intuitive because you kind of need to solve it in terms of an abstraction. So it has 2 questions, one using TXOP, which is transmission opportunity, and one without. The without is super easy, right? Because without transmission opportunity, we simply, there's 10 computers on the network, so we let them use the network 1/10 of the time, right? So if we let them use the network 1/10 of the time, so we would have guys, so we have 2 at 54, 4 at 18, and 4 at 6, right? Megabits per second. So if it's just 1/10 of the time for transmission opportunity, right?
Just put a decimal.
Yeah, we just put a decimal in there, right? Because it's 1/10 of that, because 2, 4, and 4 is 10. So the answer is just divided by each by 10, and that's their, with transmission opportunity. Because transmission opportunity says, hey, instead of dividing up by frames, we're gonna divide up by time. That's all it does. The one by frames is not intuitive. So, you have to kind of think of it in an abstraction. So you're doing it in comparison to everything else. So when you're comparing to numbers to everything else, you usually pick the smallest unit of time, right? So the first non-intuitive is, which one of these is the smallest? 54, 18, or 6?
In time?
In time, it's 54, right? So let's say that we have a unit T, which is the time it takes for a 54 megabit per second frame. So if unit T is this, 54 megabit per second frame, what is this one?
3 times the first one.
It's 3 times the first one. This is 3T, right? And this one, 9T. Is that intuitive? It kind of makes sense, right? So we pick the shortest amount of time, we set that to whatever that is, right, to a variable called T. So it's T, 3T, and 9T to send all these. And then now we have these 10 computers are sending, right? So we have 2 times 1T. That's these guys sending, right? Plus 4 times 3T, which is these guys sending, right? And then 4 times 9T, which are the last guys sending, right? That is 50T. So we now have 50 units of time to send at 54 megabits per second. So if all these guys were transmitting, right, these guys use 2T, these guys use 12T, these guys use 36T, right, to transmit. All at 54 megabits per second. So that is 54 over 50 megabits per second, which is 1.08. So that one is a little harder, which is why I said go look at the book. Does everybody understand how to reverse engineer that though now? Like given the answer, right? We pick a unit of time, which we just abstract time, right? And we say, hey, this is our unit of time, and then we do everything in comparison to that time. Remember that unit of time was 54 megabits per second. Or derived from 54 megabits per second. All right. On to the midterm. Anybody have questions on the homework? All right, so the midterm is up. It's actually already posted. It turns on at 4:15 on Friday afternoon. It turns off at midnight on Sunday. I don't recommend you wait that long. 9 days away from that. So not the following Sunday, the Sunday after that. All right, it is 14 questions, 2 hours to complete it. If you want partial credit, you're gonna have to, I can't find a way to upload things also. So if you want partial credit, take pictures of your work with clear problem numbers so I can look at them, and then set your alarm. Take clear pictures and send it. It's in the instructions are in there. Send it with CSLec18 5220 midterm work with a subject line. And that's in the instructions. So otherwise, it is some multiple choice, some true and false, and some numbers. If you get everything right, exactly right, you will just get your grade, right? You'll get a grade anyway, but presumably you will know if you got 100% right off the bat, right? If you don't get 100%, then I will look at your work and add points back for problems that you missed.
So there's multiple choice.
Multiple choice, a lot of numerical answers. Fill in the answers, fill in the blanks. So the numerical answers allow me to put like a plus or minus on them. So some of them have some pretty generous plus and minuses. The problem with that is that there's no way to really do that if it's a plus or minus order of magnitude, right? So if you're doing your work and you're like, oh, 10, the speed of light divided by, 10 to the negative eighth is 10 to the negative 12. Oh, it's not, right? Right, so 10 to the negative 16th, but you just messed up. It's a small math error, but it just has a large propagation result. So I need to look at your work. There's no way for me to figure that out otherwise. So if you get it just flat blankly wrong and it gives you 0 points, I will go in and look at your work and add points back. So
For the fill in the blank, does it take 10 times, to the whatever negative or positive power?
now for all the ones that are just numbers, it's just a numerical answer.
Okay.
I tell you in every question, I want the answer in milliseconds, microseconds, gigahertz, megahertz, so pay attention to that, because otherwise you'll be more, some factor of 3 orders of magnitude off, right?
Rounding?
Huh?
Is there rounding?
So the rounding thing is the plus or minus. So I was pretty generous on the rounding things.
And does it say how many decimal points you have to go to?
No, none of them say that.
So just
Most of them are clear, definitive answers. There's a couple of them that have decimal points in, but not many. And if it does, then I do plus or minus the next digit up, right? So, which should take care of the rounding. But if it doesn't, I'll just look at it. It's no big deal. So, what's the relationship between relationship of Hamming distance between the number of errors that can be corrected and the number of errors that can be detected?
Isn't it 1 minus the one that can be detected?
So detected is d minus 1, right? So, but what is corrected? It's 2d minus 1. So the relationship between the two of them is, if you can detect one error, then or correct one error, you can surely detect 2, right? So you can always detect double the errors. If you have a checksum and a CRC, what is the value of each? Why would you use a checksum over a CRC, vice versa? Give me pros and cons of checksum versus CRC.
Checksum's fast.
Checksum is fast. Why is it fast?
It's easy to calculate.
It's super easy to calculate, right? It's all additions and shifts, right? Which computers do in usually 1 clock cycle.
You can detect less errors with a checksum, right?
You can detect less errors. Why? If you had an 8-bit checksum and an 8-bit CRC, why can you detect less errors in it's an 8-bit checksum, an 8-bit or 8-bit error detecting code? Why is one better than the other?
The checksums can cancel each other out.
Yeah.
If you get 2 errors, you can cancel each other out.
Right. Yes. Right. CRCs are much more robust on that. What else? In fact, today, if the internet was being designed today with today's computing power, nobody would use checksums. Right? Because while CRCs take more computations, they can still be done with shifts and subtractions. Modulo 2 subtractions, right? It just takes more rounds to get through there than a checksum, right? Nobody would use checksum. The problem is when the internet was designed, the routing devices were really, really low processors, right? They couldn't handle that kind of stuff. Any other pros and cons?
So CRC requires more resources?
It does require a little bit more resources. Yeah. Anything else? CRC, more resources, checksum, less resources, right? CRC is more robust given the bit size, checksum is less robust, right? Give and take. And checksum faster. So generally overall, which is something a little bit different than resources. Because it might, if you had intermediate devices, you might be adding on network time, right, to get them out, if you were checking. None of our modern networks, they don't check in the middle, right? Know how to do a CRC? A small one, so there's not very many errors. But know generally about CRC, know generally about checksums. Know about seizing a line, how to add stuff up together. Why files should be either, why frames should be long or small, what the pros and cons for both of those are. Actually know that pretty in depth. So, in fact, if I had a network that looked like that, everybody see that? Without seeing the words? Right? So you have a source and destination with two intermediate devices, right? Right. If you had that network, right, which we drew up on the board right there, right? What are the pros and cons, and how do you calculate how long it takes to get across with different packet sizes?
So how long it takes to get across with different packet sizes?
Sure. Yeah. How to do that?
So it's similar to like what we did earlier.
Mm-hmm.
Okay.
What is when I say latency of a network, what does latency mean? It's the delay. So in a contended network, if I ask for the length of a contention slot, what does that mean? Is that length a measure of time or a measure of distance?
Time.
It's a measure of time. So the length of a contention slot is what? We talked about this. Actually, you guys were working it on the board when I got here.
2 times the bandwidth.
2 times the delay.
So that's the seizure, the time to seize law.
Time to seize, right? Contentious law is the time to seize in that work. Don't be afraid if you have some really big numbers. And don't be afraid if you have really little numbers. So, just don't be afraid. No bit stuffing and or no byte stuffing. What's the advantages of byte stuffing over bit stuffing? And disadvantages? Which one's more efficient? Bit stuffing or byte stuffing?
Byte stuffing.
Oh, bit stuffing. So,
Well, at least you're wrong.
so bit stuffing is more efficient with respect to, bit stuffing is more efficient with respect to message size, right? Because you don't have to land on a byte boundary, right? So if you're doing bit stuffing, you could pick 3 bits or 10 bits, or like it can be, you can just pick something that's more efficient for you depending on how many flags that you need. Byte stuffing is less efficient with respect to message size because you have to land on a byte boundary. So computationally wise, though, it's probably the other way around, right? Because in a computer, everything is moved by bytes, no matter what. So if you want to move 1 bit around, you have to move the whole byte that's around it, even if you're only going to use 1 bit. So, like, for instance, let's say you say, oh, maximum efficiency is 9 bits. Well, it's not so good, right? Because now you have to move 2 bytes, and now you have to mask off stuff, and so computationally wise, it's a little different. But know how to basically do that problem that we just did.
That one or the escapes and the flags?
The escapes and the flags.
Escapes and the
Oh,
flags.
sorry. Yeah, that's the difference.
I was wondering.
Know how to do that one too. Yeah, know how to do that one too. Know how to do simple CRCs, know how to do the Hamming coded message, know how to convert from hex to decimal, right? Simple computer science stuff. Mainly because there's no way for me to put a hex numerical answer in Canvas. Otherwise, I'd just ask for it in hex. Be way easier. But then if I ask for it in hex, or like a fill in the blank answer, then I gotta contend with 0 X's and lowercase and uppercase, and it's awful. So some of them I just ask for a decimal number, which is converting from hex, because I can make a numerical question that way. Oh, and that problem that everybody hates, which is being able to figure out bandwidth. If I gave you 2 wavelengths, be able to find the bandwidth between them.
And you
For-
mean microns?
Huh?
Microns, like the actual length.
Correct. I give you 2 wavelengths. For instance, if I said something like yellow light is X to whatever, to Y in wavelength, right? What's the bandwidth of yellow light? Huh? Oh, no, like bandwidth is in hertz.
Oh,
Oh, it's the one hard question on there. Everything else is super easy. I'm gonna get back like 5 100s and 4 90s. All right, so technically our midterm is all of next week, right? But I think we should have at least 1 class. I'll give you a class period to do your midterm, because sometimes people just have schedules and you need that time, right? So We can do it, either the class period could be Monday or Wednesday, and essentially what I'm asking is, what day do you want off to do your midterm?
Taking off Halloween would be nice.
Wednesday, that's what I was thinking. All right, so no class on Wednesday next week, because you're doing your midterm that time. All right.
Sure. Is there gonna be anything related to satellites or wireless?
Yes,
Okay.
not on the wireless. Wireless is awful. It's hard for me to grade too, because you got like all this chicken scratch on top of each other, trying to figure out things. So there's stuff with satellites. But the question for satellites is still pretty simple.
Anything related to the, like the hidden terminal problem or the?
Nope. Like I said, I think the test is really easy. So there's stuff with satellites, but generally it's figuring out like delay and stuff, like the simple questions with satellites.
And it's covering through chapter 4?
Yes. And then the final will be comprehensive, but it will tend to stick mostly on the networking and transmission, or transport. Huh?
Throw us some easy.
Throw us some easy ones from earlier, yeah. And it's very likely that our final will also be online, because it's looking like I might on December 10th have to go to California. So. All right.
And I could get that done. Submitted. Thank you. I'm on the road from here. I might be here on the weekends, but that's about it.
All right.
So
Good luck. Congratulations on the new gig.
Yeah.
Just particularly when it becomes a home gig.
Yeah, right? That'll be sweet. Especially for classes.
How often have you ever worked on before?
Once for NASA. I think I was there for 9 months.
Okay.
Like the best job I ever had.
So you figured out how to like manage time when you're like at home and
Oh,
everything?
yeah, yeah.
Can you watch the kids? Can you go get milk?
Yeah.
They still have a stupid affinity for typing my answers. You don't mind if I type the midterm?
Oh, no, it's just on the blank.
Okay.
Like,
Cool.
yeah, you'll type in the answers or
Oh, it's like physically on the.
physically on there.
Okay.
On the campus?
Not
Yeah.
the other way. Okay. That makes it easy.
Yeah, you'll see. You got it. Once you started at a certain time, you got 2 hours to finish it, and it's literally typing in and hit enter,
Okay.
and it gives you a grade at the end.
I was
Which,
thinking